We're just about ready to get started with our webinar. Thank you for joining us. Good afternoon and good morning, colleagues. I am Sherry-Ann Farquharson, the Knowledge Management and Capacity Development Expert for the Caribbean Center for Renewable Energy and Energy Efficiency, CCRE. Welcome to the Regional Universities Networking webinar. The Regional Universities Network, or the RUN, is a network of excellence for sustainable energy research and education. And the primary aim is to enhance the knowledge and capacity that is required to support innovation within the energy and energy-related sectors in the region. Today's main presentation is from Dr. Anil Ramkalawan. Dr. Ramkalawan is an assistant professor at the University of Trinidad and Tobago, UTT, and is currently the discipline lead for the BASc in Manufacturing and Design Engineering program. He has worked at the university for over 10 years, during which he obtained his PhD. His doctoral work from the Manufacturing and Design Engineering Department was in the area of controls and renewable energy, with specific interest in ocean wave energy devices and simulators. And we'll be hearing more on that today. Anil also has a BSc in Mechanical Engineering from the University of the West Indies. A few housekeeping matters before we begin. At the end of today's webinar, we will invite you to participate in a feedback survey. And when you exit the webinar, it will pop up as a web page. Your feedback is very important to us to help us to improve on our offerings and also to hear more about what you would like to hear more about. And so we ask you to look out for that when you are exiting the webinar. To participate, use the raise hand feature if you want to ask your question live, or if you would prefer, you could write your question in the Q&A and we will read your question and allow Dr. Anil to respond. And at this time, I will hand over to Dr. Anil Ramkalawan.
Thank you, Sherry-Ann. Good afternoon, everyone, and I would like to thank CCRE for this opportunity to present our research thus far in ocean wave energy, and also thank you, the audience, for taking your lunch break to listen to this presentation and engage in some discussion. All right, so I will now share my screen. All right, is it visible? Is everyone seeing that?
Yes, we can.
All right, thank you. All right, so today I'm going to present the ongoing research on ocean wave energy research at the UTT. All right, the overview. All right, we'll have an introduction, some previous work, the rationale, some background, our targeted research area, how we accomplished that, some results, conclusion, and our scope for future works, and some acknowledgements. Alright, so in our Caribbean region, SING in 1998 concluded that our wave climate was a low to medium energy density resource, right? And this ranges between 12 to 35 kilowatts per meter of wave. Gleich in 2006 stated that countries that had a 767 meter cube per year per capita of water was considered to be water scarce. Now, that being said, that will include most of our Caribbean islands, right? And most of them has resorted to, let's say, desalination via a reverse osmosis process to try and meet that requirement, right? But this process is, however, very energy intensive, and due to that energy intensity, the cost is high, right? So, unlike Trinidad and Tobago, which has oil and gas as our resource for energy, they have to import, right? And therefore their costs for energy, significantly goes up, right? So therefore, it seemed logical to try and maybe couple, our wave energy resource in the Caribbean here to reverse osmosis desalination to produce fresh water. Now, this was realized by my supervisor, Professor Prakash Prasad, since in the 1980s, where he started this sort of research. Right now, since then, Singh, in his research in 1998, also concluded that our wave directional coefficient here in Trinidad is around 0.42, and further concluded that even cylindrical devices were best suited for this sort of wave climate, right? And that was particularly for point absorbers, even point absorbers. And we also have to remember though, that this is mainly due to our northeast trade winds, right? And these are wind generated waves. So this led to a simple proof of concept where a student looked at a heaving buoy connected to a lever attached to an offshore platform, and this was essentially for the purpose of driving a hydraulic pump to produce pressurized seawater, and it proved to be successful, right? So it worked. Chedi in 2004 went on to do a theoretical analysis on that system, and he came up with a optimized design for a buoy connected to a lever system connected to the cylindrical heaving device. So the next logical phase or step with respect to this research was to design and build a prototype and have it tested. But locally here, or even in our region here, Caribbean, we don't have access to testing facilities, right? A wave pool with instrumentation. Our only avenue for testing is mooring the device out to sea, right? Now, in the initial stages of testing, this can be very costly. You have to get a boat, you have to get a crew, you have to get your instrumentation, and so logistically it's very difficult initially for testing. So this led into the research that I am looking at, and we decided to look at a lab-based simulator, right? Where in the initial stages of a prototype, you can do initial testing, proof of concept, and in the later stages when a lot of the issues have been ironed out, you then finally take it out to sea. So we went on to this venture in terms of developing a waveforce simulator for lab use. All right. Now, to further back up this, the reason for this lab-based simulator, we looked at the research. Right. So here we have a heaving wave energy device. Right. This was created by Elwood in 2009, called the Sea Beagle. Now he was going to take it out to sea, right? So you'll see the crew, you know, he got access to a ship and also his instrumentation and stuff like that. Now, just before taking it out or mooring it out to sea, he decided to test it on the pier. So you'll see here he loaded it on some blocks and decided to have a crane actuate the device, right? Just to ensure that it was working before mooring it out to sea. Now it was working, but you have to remember that a crane will only manually move up and down, yes, but not with the same rhythm as as on the ocean wave, right? So after taking it out to sea now, he realized that no relative motion was observed. So meaning that it wasn't working after they placed it in the area it was designed for. And later on, it was determined that something had failed within the device. Right now, this could have been prevented if it was tested in a lab, or onshore, and saved a lot of time and cost. Right. This next slide here shows testing facility, right? Wave tank testing Salters Dock. Now, you can see this how large the area is that is required for the wave pool. There's a lot of instrumentation required and a lot of cost associated with that, right? So, and again, we don't have access to that in this part of the region. And devices that we are looking at again is heaving devices. Cunahan and Knight back in 1998 quoted the cost of a wave pool was $80 per square foot, and that is in US dollars. And that was to only build the wave pool, right? It didn't include the cost for instrumentation, right? And the requirement for that space was about 20,000 square feet. Later in 2016, there was Wave Garden who estimated the cost of a facility inclusive of the wave pool and a wave generator, and they estimated around 6 to 7 million euros, right? So the cost is always increasing, right? And remember, it requires this large area, this large space. So hence the rationale for this lab-based simulator is very necessary for prototype development, right? Even wave energy prototype development. Some of these devices we have here as that was developed and tested out at sea, right? We have the Delboy back in 2006. We have the Aquaboy from Pinavera Renewables, right? The Delboy operates on the principle of even motion, again, pressurizing seawater via a linear pump to produce fresh water. So it uses the heaving wave energy directly. The Aquaboy uses it indirectly, where the energy is converted to electricity via some sort of generator, right? Now we do have devices also that that have been theoretically designed but not built, right? This first picture here shows a heaving buoy connected via some geared shaft that is turning a generator to produce electricity. The second picture here shows a heaving device again connected via some sort of pulley system, which is also attached to a generator, right, creating electricity. And if we had a simulator again in a lab, you can test all of these before taking it out to sea, right, for initial testing, right? This last picture here shows a hydraulic system that is being driven by a heaving buoy connected to some lever system again, right? So all of these could primarily be tested in the lab to determine some of these or to optimize, right, in the initial stages, right? So this chart here sort of narrows down our area that we looked at, right? And this was to create the waveforce simulator for lab use. All right, so we looked at we are looking at renewable energy under our energy options, right? We are targeting ocean wave energy, and if we have a buoy on the ocean wave, it will experience 6 degrees of freedom of motion, right? And we are looking at particularly heaving motion, the up and down motion. We are looking at deep water waves, right? And rather than shallow water waves, right? Deep water waves tend to be more consistent, right? They are more sinusoidal in pattern, right? They have more energy, right? And they tend to lose energy slower than shallow water waves, right? Waves tend to lose as they approach a depth of less than half a wavelength, due to that the orbital or circular pattern of the particles. They start hitting the ocean floor, and this causes them to lose energy. Right, so we are looking at the deep water waves. In terms of the design criteria, we decided to look at direct pressurization, right, via reverse osmosis for desalination. Right, so mechanical pressurization of the seawater for reverse osmosis. And finally, now for testing methods available. I mean, yes, you can test it in a wave tank, but we don't have that available. We only have open sea testing at this stage. So our gap that we are trying to fill here in terms of the research is designing a wave force simulator for the lab. Alright, the way we went about this, right, so we looked for we simulated a theoretical model of a buoy connected to a wave energy extraction device, validated the model, determined the characteristics for the physical design. We also looked at a proof of concept, design and fabrication of the prototype, and then we needed to create a controller for that actuation device, and finally validation. So the model that we looked at an existing model, right? This device here was created by Masuda and analyzed by McCormick. This is a pneumatic wave energy converter. So this device harnessed energy via the heaving motion of the surface of the wave here, or the water. The air above it, due to that heaving motion, is forced through a turbine generating electricity. So McCormick created a model, and we looked at this model, and what we wanted out of this was the heaving motion of the buoy, and we wanted to use that heaving motion to feed into our lab-based device. So he looked at a spring mass damper system approach to model the system, and we took that model now and simulated this on the MATLAB Simulink software, and we compared the results now to ensure that our model was producing the same result as McCormick's. So you will see his results here being displayed on the right, and we are looking particularly at the Z subscript B here, which is the heaving displacement, right? On our model here, our response displacement is this red line, right? This blue line here is the input wave data, right? So they were comparable, and now for that part of that phase of the project, this part now will be fed into the lab simulator to replicate. Alright, so our design requirements, right? So we got wave data from the southeastern coast, right? From a company called Coastal Dynamics, and this was off the coast of Guayari. So we looked at the average wave height and associated periods that would be fed to the model and then into the prototype to replicate that heaving motion. Right? We determined the speed of the actuator, the sort of forces required, and the forces required now was determined based on the application, and the application we chose was direct pressurization for reverse osmosis. We looked at membranes, Torre membranes, and we looked at, that those membranes operate on 800 to about 1000 psi. So we looked at that range. Our wave height and associated period was 1 meter and 8.5 seconds, and our type of motion required for the simulator was sinusoidal. Right? We decided to do a proof of concept using Simulink again. So we built a hydraulic system from Simulink just to ensure that we can, or it is possible, to get a sinusoidal output from this hydraulic rig, right? And we chose hydraulic. I mean, we went through the design process, and hydraulics was determined to be the best suited for this application. We were looking at the high forces that output we can get from a hydraulic system, the speed and ease of control, right, for an incompressible fluid, right? So let's say oil versus, let's say, a pneumatic system where air is compressible, and you'll have that difficulty in controlling the motion, right? Now, to ensure the sinusoidal output again, we looked at a sine wave input initially for this model here, and you can see the results here for the input versus the output, right? So it was following a sinusoidal output. We also verified this using another software called Automation Studio, right? We also sized the components of this rig using some of the software and through consultation with various hydraulic companies, right? And this here was the result of those tests so far and design, right? So we have our hydraulic pack here circled in yellow, and our actuator, right? We have a 1 meter double rod, double acting cylinder and frame, right? So double rod, we use a double rod here so that the volumetric displacement on either side of the piston and cylinder arrangement would be the same to control the speed, right? So our speed will be the same on both sides, right? And also attached to this rig now, later on we attached our instrumentation to let's say monitor our pressures, our forces, and our displacement mainly. Right now, for the operation of this rig, or the control, we needed to design a controller. Right? This small yellow circle here shows, our computer software, our input-output cards to interact with the hydraulic rig, right? The servo valves, our amplifier cards, and all our signals. All right. The second larger circle here shows a pulley system, which was designed basically to simulate right now a heaving device. So we attached some weights to that cable, which was directly now attached to the hydraulic ram, right? And this was again to simulate a device on the rig to simulate that motion. Right now, to design the controller, we needed to find our transfer function, or our overall transfer function for this plant, right? And we looked at a black box model approach, and what we did now, we conducted some pilot studies on a known laboratory piece of equipment, right? And we applied the entire process to that known rig for validation. So we went through the entire process because of the moving directly to the hydraulic rig. We, due to the cost and all that, we did not want to damage any of the equipment, and we wanted to have our procedure outlined, or our SOPs. So based on those pilot studies, we came up with an SOP to follow and implement on the rig to come up with this transfer function. Right, so how this black box model approach works is that you will send various signals to your unknown rig and observe the output. We will record that data and have that input-output data, and we'll feed that into some sort of system identification toolbox, and that toolbox now provides various transfer functions that you can now test. Alright, so we use sine waves, square waves, and sawtooth waves, right, from our signal generator. And this is just a sample of the data, the input and output data here. So the top graphs show here the input, bottom showing the output. Alright. This is just a sample of some of the transfer functions that were developed from the system identification toolbox. Alright. These transfer functions now, we did some simulation, theoretical simulation again on Simulink to try and get responses. So we did a step response approach, right? Using normal control theory. And this was done to observe the response characteristics, rise time, settling time, overshoots, right? And try to tune our PID values. Right, so here's just a sample of some of the gains, PID gains that we would have simulated. And following that, now we identify the response characteristics. And we chose now from this the best characteristics, right? Meaning, our set rise times, our percentage overshoot that we did not want to cross, and our rise time. We then now use those PID gains now and applied it now to the physical rig to see how it will respond, right? And here now this graph here shows, this green line here shows the output from that hydraulic rig, right? So this is just a step response, and you'll see a red dotted line here that that was the simulated response. So from the values here, they were reasonably close and within our tolerance. So we decided now to apply our sinusoidal input, right? So we did a lot of testing and we tried to do this in phases where, just to reduce our errors. And, it being hydraulics, we did not want to damage any of our equipment, right? So again, we simulated theoretically based on those gains. And you can see here our percentage error between the input signal and our output was 0.04%. Right? Due to that low error, we said, well, okay, that is okay to apply to our physical rig. And we applied it to our rig. And this is just a snapshot of some of the graphs. So input is our blue line, and our actual response from the rig was the green line. Now you'll see various steps here up to 5 volts. All that shows is that we use the midpoint of our cylinder as our still water line, right, on the ocean, just to represent or simulate that on the hydraulic cylinder. So if we went from 0 and apply that signal directly to the hydraulic rig, you would get a large overshoot. So we took it in smaller steps just to avoid that large overshoot. So you'll see a smaller overshoot being obtained here from the rig at every step until we reach the midway. And then the sinusoidal input was applied, and we got a percentage error of minus 0.173, right, which was fairly low enough. And what we decided to do then now was to apply our theoretical buoy model, that output now from the model, to see how the rig responds to that. Right? So we send that input signal again. Our input signal here is the blue line. Our actual output from the hydraulic rig displacement is the green line, and you will see here we looked at the error, right? The difference between them, right? Our percentage error was 2.29%, right? So it was fairly close, right? And I posted here a snapshot between 380 seconds and 405 seconds. So this is just a small snapshot at this area here, and you can see how closely the rig was following that input, right? So our conclusions from this, this design, or right, a new device was developed and a new method of testing was proven. Development of the control of operation of this hydraulic actuator was within a 3% error, right? That could further be reduced with more, let's say, more testing in terms of or tuning the rig. What we noticed though, to form the transfer functions, sawtooth signals generated, the best transfer functions for this hydraulic plant. So that was interesting, right? So compared with our sinusoidal inputs and our square waves, sawtooth waves, we trace back that, we got our best responses for those transfer functions. Now the test bed that was created here was for a 10 centimeter range. Obviously our wave climates change consistently, so we can have different, let's say, range of operations depending on our wave climate, right? And obviously now that that is our wave heights and our wave periods, we can vary that. And our rig max is 1 meter, and we can still vary our speed via our servo valve. The hydraulic simulator provides the main requirement for testing even wave energy device, right, based on the inputs. Well, water isn't required for this device, as in the wave pool or testing out at sea. All right. What we also realize is that if you are testing a device, you can also test the lifespan in terms of applying various signals or continuously to see how much cycles your device can last, right? And this will help in terms of, let's say, maintenance later on when your device is placed out at sea, right, for routine maintenance before failure. All right, so future work and work that we are continuing right now, right, the input of the rig can be replaced by a real-time data buoy, so via some wireless mechanism. So let's say you are designing a device for the northeast, or let's say off the coast of Tobago, where we have much larger waves, and you can place, let's say, a data buoy there, and let's say we feed data directly to your lab, right, where you can have real-time testing. And the more testing we do in the lab, the longer, or the less testing you have to do out at sea, right? You can save lots of time and money. Development of the mechanism to automatically select the tune PID gains, right? We can have various ranges, right, for depending on the wave climate that you are targeting, and that is something we are trying to look at also. We also want to create a database of different areas around Trinidad and Tobago, where if you are designing a device in a particular area, once we have a database, we can automatically just start testing in that area, right, in the lab. The next phase of this project is to actually now have a device designed and tested, and eventually conduct sea trials in our later stages. At this stage, I just want to share a short video of the rig, of the working rig, right? that video, you can just observe how the control application, you'll see the cylinder here slowing down as it approaches the change in direction. So you can picture as the sinusoidal input is being sent, it starts slowing down as it approaches the change in direction, right? Following our input wave pattern. All right, just some acknowledgements. I'd like to thank UTT for providing the resources for this research, BBTT for funding, right, this research project, Postal Dynamics for the provision of the wave data. We needed actual wave data. Professor Prasad for his guidance and vision for this project. Dr. Sangster for her mentorship throughout this project, and that is also still ongoing. The mechatronics group at UTT, my wife, family, and friends for your encouragement and support. Thank you for your time, and I will now entertain any questions that you all may have. Thank you.
And thank you, Anil. That was quite interesting. I really do like to see where we're moving to more independence in the region, so we are not able to set up the expensive wave labs, and so we use what we have and to simulate the conditions so that we can get the answers for ourselves. So I really do like that aspect of the work. I'm inviting colleagues you can enter your questions in the Q&A. If you'd like to ask your question live, you can raise your hand so that we can have quite an interesting discussion on the work that's happening. To kick us off, I'm going to hand over to Miles Harrison. Miles is actually doing some ocean energy research with us in the SICRI as an intern. And Miles, I'll allow you to ask the first question.
Thank you, Sherry-Ann. So I was wondering particularly why it is we would focus on the heaving motion as opposed to all the various different types of wave motion. So you have like the rolling, etc. Pitch we could have looked at as well. Why specifically the heaving motion? Why not look at like another type of oscillating body system that could possibly focus on like a device within a frame that kind of it interacts with the whole body so that it uses every aspect of the wave direction, as well as you think that this type of device is more efficient than, say, something that would use the other types of motion?
All right, so what we did so far in terms of the previous work that was done, studies were done, due to our directional coefficients and, generally our wave climate. And what we did, we took the conclusions from those research, right? And they basically concluded that heaving wave energy point absorbers were better suited for our wave climate, right? And again, this is due to our northeast trade winds, and targeting that particular motion, heaving motion. Now, we do have we do have at least one or two students who are looking at other motions, but to say that if one is more efficient than the other, I will argue that point in terms of, it really boils down to the design of your device and which sort of motion it is going to target. All right, I hope that answers your question.
Yeah, that was very helpful. Thank you.
Thank you for that question, Miles.
No problem.
All right, I'm seeing a question in the chat from Gerald Bisnath. Could this approach be applied to a cylinder array to replicate the other degrees of freedom as well?
Yes, and that is a good point in terms of, if you have an array, let's say, you have a wave that is passing, right? And rather having, let's say, one device, it will absorb some of the energy. But whereas, if you have an array, you can capture as much energy as possible as each wave passes, right? Now, in terms of long-term effects, we have a lot of, in the Caribbean here, we have a lot of, let's say, coastal erosion and things like that as well. Now, this might be a little far-fetched, but, the more energy you try to, let's say, absorb, will be the less energy reaching, our shorelines and these kind of things, right? So having an array, I will say, will be the best option in terms of capturing as much energy as we can as each wave passes.
Okay. All right. I've never actually thought about wave energy and that's possible positive impact on the environment. Never actually thought about that in terms of absorbing some of the kinetic energy before it reaches shore for erosion.
But you have to remember too, we spend a lot of money on creating seawalls, right, to prevent coastal erosion. But why not try to absorb the energy, right? Divert some of those funds into some of these areas, because as Miles pointed out as well, we do have a lot of different types of devices, right? Apart from capturing energy on the surface, we have beneath the surface, and we also have shallow water devices, that are created on the shorelines, right? Based on, let's say, the blowhole effect, where you have waves crashing into a blowhole, and what they do is try to have a air turbine with that air passage capturing that energy and converting it into electrical energy.
Okay. All right. Miles, I see you have another question.
Yes, I was wondering how do you think this type of device would compare to something like the Pelamis?
Right.
Which is, yeah, if you're familiar with the device. I'm not sure if you're familiar with
it.
Yeah.
So
okay.
Yeah, so the Pelamis, right, so that is a very, very huge device. It was, I think, initially designed for wave heights between 3 and 6 meters, I believe. And following up on the question before, I believe that is capturing both heaving as well as I think it's the swaying motion, because that is made up in 3 or more parts, where each joint, there's a hydraulic ram connected to it. One is vertical and one is horizontal. And when I say vertical, it is not 90 degrees, but it is at a particular angle, similarly to the next hydraulic ram, so that it captures energy both on the heaving and I believe
on the sway.
Yeah. So as it is so remember, it is fixed to the ocean floor. So as the wave passes, it sorts of move in a snake-like
pattern, right?
Yeah, capturing that energy. So I know that one was basically designed for that wave climate, but I'm sure that the design can be, let's say, implemented for our smaller wave climate here, right? I mean, our average here locally might be was around 1 meter, right? 1 to 2 meters, sorry, right? With periods between 9 and 12 seconds.
Okay. And you think it would function better as a hinge or a ball and socket joint?
Well, you have to remember, alright, so in terms of that Pelamis, work is still ongoing. I mean, when they started, they were looking at capturing, I believe it was 10 to 20% of the energy. And over the years, they have tried to optimize the design to try and capture more and more energy, right? And based on testing and I will say further testing, they can improve that. But with respect to what you're asking there, if the hinge or having a ball and socket will be more efficient, I believe that you'll have to do some theoretical analysis as well as some initial testing to determine that.
Okay, thank you.
All right, following up on what you said in terms of the wave heights that are available. My first is a two-part question. The first question is, how far offshore? Because I know you mentioned that you're doing deep water waves because you want less of the, let's say, the haphazard motions.
Right.
So how far offshore would you be getting that kind of 1 meter, 8.59 second periodicity?
Right. So so this company, Coastal Dynamics, that provided the data, they normally gather data for these offshore platforms for design, and they provide that data to companies that go into the design of offshore platforms and stuff like that. So basically, the depth will be greater than the wavelength of these waves, right? So we are looking at least more than a kilometer out at sea, right? This data was captured. Yeah.
Okay. All right. So I need to wrap up my questions because a couple questions coming in the chat. So I'll try to wrap up mine quickly. About that 1 kilometer, that's a pretty good distance in terms of carrying that energy back to shore. So
Yeah.
that is definitely going to affect costs. So the second part of my question was about cost and possible output in terms of megawatts. What size plant do you think could be put out there? I know that you're still testing in the lab, but what are you aiming for, and how much do you think that's going to cost to get that power back to shore?
All right. So what we looked at when we now got that data, right? It was a year's worth of data. With data again is classed according to the seasons, right? The 4 seasons, and we found the averages for each season, and also found the overall average over that period of the year, and we found it to be around 25 kilowatts per meter of wave based on that data, right? And this is per meter of wave. So again, if we are setting up, an array as one of the questions for Gerald Bisnat, you depending on the amount of devices will determine your output, right? And again, transmission lines under the sea to take it back out, to take it back to land, right? Now, again, initially this project started with respect to producing fresh water via desalination, reverse osmosis. So, the thought process behind it back then was to supply offshore rigs with fresh water, as well as, let's say boats and stuff like that out at sea. So, the power part of it will be, we are getting into it, but that will be different designs then, per se. Yeah.
Okay. All right. It's always good when you can get more than one outputs.
Correct.
So definitely appreciate that. All right. So Gerald has another question. How adaptable is the model that you have developed to represent the different wave seasons and perhaps extraordinary events such as storm waves?
Right. So there's a lot of thought process that is happening throughout the world with respect to these unpredictable conditions, right? Storms, rogue waves, and some companies are looking at trying to design for those sorts of events by because if you try to design for the worst case scenario, cost significantly goes up, right? What they're trying to do is look at ways that could, let's say, reduce that cost. So let's say not go into the far-fetched region and design for the lower end, but maybe have contingencies. And I can give you an example for one. Let's say you have a heaving device, right? And you have that buoy. Most of the time it is connected to the device, and what they are trying to do now is submerge the device under the water, right? They will design the tether. So if it let's say the wave forces passes a certain critical range, which means if we have a storm or again rogue waves, it will break or fail so that the device itself that remains under the water is not damaged, and the buoy is more or less a sacrificial buoy. So the cost versus the entire device could be reduced. So there is a lot of work happening in that area to reduce that cost.
Okay, all right, thanks. So it sounds like it would be quite adaptable when you're finished. The next question, it came in from Jean-Michel Parle. He appreciates the presentation and insights into your research. When designing for such inhospitable operational conditions as offshore, how early do considerations of resilience, durability, and longevity come into play in the design and in the specific mechanisms selected for investigation, research, and testing?
Right. So in terms of the design, remember, out at sea again is a corrosive environment, and again these unpredictable weather conditions, storm, rogue waves, right, surges. So what I will think of in terms of having this lab-based device, we can look at number of cycles it could withstand, and having or develop some sort of control or instrumentation where, if we have various sensors around, the environment where the device is being placed, where, as it senses, let's say, these extreme conditions, it can send signals to some sort of device that will either retract it, if it's a surface device, retract it below the sea to protect it. Again, maybe have, like the sacrificial buoy, or depending on design, you can implement some sort of control device to prevent your damage to your device and or even loss of your equipment, right?
Okay, all right. So you're designing for resilience while you're in the lab.
Yes.
Okay. All right. I have one other question. I found it interesting that when you were testing the transfer functions, that the sawtooth waves gave better response than the sinusoidal or even the square waves. Have you come up with any theories or understanding as to why that would be?
Well, based on the black box method and the approach, they normally send any sort of signals, let's say, to your plant, right? Regardless, this plant just happens to be a hydraulic plant, but based on our signal generators, we had available the sawtooth, right? You can send other signals, yes, and you can also build your own signals, right? So what I wanted to do in the long term, and this will require more funding, if we have data boys where we can get real-time data, and we can send, if you are designing for a particular area again, be it the east or the north coast, we situate that data boy there and send signals to the lab where the rig can, follow that signal. Now, in terms of the input, I think the closer the input signals that we are going to, test the device with, I think we can get closer transfer functions or more accurate transfer functions based on that. Why sawtooth waves work better right now, I cannot say, because we did try sinusoidal waves, and we assumed at that stage that it would have been closer because the output required would have been sinusoidal. But that proved that theory did not hold.
Okay, all right. Well, I look forward to hearing when you answer that question.
Yes.
And very interesting work that you are doing. Definitely want to hear more about the next steps, and to see if we can move from out of the lab into implementation, and then the lab is available for testing for other devices that could be designed. So definitely appreciate your time, and thank you, Dr. Ramkalawan, for sharing with us today. And thank you to our participants for being here and joining in on the discussion. For the month of November, the Regional Universities Network will be joining with CARICOM Energy in the activities for CARICOM Energy Month. And so we will not be having our regular run webinar, but we will join in a Green Table Talk series. And the session that you'll be invited to will be presented by the University of Guyana. They've been doing some work with the Caribbean Examinations Council on greening the syllabus for the non-energy subjects. It's quite some interesting work, and we think it will help to better prepare students when they're coming into university or going out into the world of work. So we are definitely looking forward to hearing about what the University of Guyana has been doing with CXC, and you will be invited to join in on that table talk discussion. As we wrap up, I remind you to complete the survey so that we can get your feedback, and also have a good rest of the day and a good weekend ahead. Thank you very much for joining us.